Hi everyone, my name is Vladimir Shakirov, and I'm a machine learning researcher at Happyverse. This presentation provides a general overview of talking head generation approaches with lip synchronization. So let's move on to the next slide, where we see the three main approaches in video generation: diffusion models, NeRF, and GANs. This slide presents generally accurate statements, but at the same time, the disadvantages are somewhat exaggerated and stereotypical. These are more like common perceptions that, in recent years, have started to fade. For instance, it's often said that diffusion models, while high in quality, which is true, are very slow and can't be run in real time. However, recent open-source projects on GitHub show that real-time diffusion is now becoming possible. Similarly, NeRF is typically associated with the need for many images from different angles and slow rendering, which is mostly accurate, but recent methods have made significant progress on that front as well. So generally, NeRF requires an extensive setup with images captured from many different angles, as shown in this picture. Here we see a drum set surrounded by cameras from various viewpoints. However, there are also approaches that allow us to reconstruct a fairly decent 3D mesh from just a simple webcam video, especially if the person turns their head left, right, up, and down. While the quality may not reach the level NeRF typically delivers, it can still be quite reasonable and visually convincing. Let's talk a little bit about Gaussian splatting, which is not exactly a type of NeRF but is closely related. In this approach, the scene is represented as a cloud of 3D Gaussians, without using neural networks. It can run in real time, although the output quality is somewhat lower compared to NeRF. We can also see on the Tavis website that they consider this switch to Gaussian splatting to be a significant improvement. According to their post, moving from NeRF to 3DGS helped them achieve good visual quality along with real-time generation speed. The difference between NeRF and 3D Gaussian splatting is illustrated here in Figure 3. In the case of NeRF, a neural network is queried along each ray. You can see there's only one ray per pixel on the screen because of the pinhole camera model. In contrast, Gaussian splatting doesn't use neural networks at all. It simply blends a set of Gaussian entities along the ray to produce the final image. So let's move on to MuseTalk, which is a solution based on generative adversarial networks. Here we can see that facial identity isn't fully preserved. On the left is the original image, and on the right is the lip-synced result. You'll notice that the lower half of the face isn't fully retained. Features like the beard are missing, and the lips don't quite match the original. However, what's particularly interesting is the real-time performance. 30 FPS at a resolution of 256x256. And by resolution, they specifically mean the size of the generated face, not the full frame, which may be significantly larger. What's particularly interesting is that they use just 8 NVIDIA H20 GPUs, which are a weakened variant of the H100, and trained the model for only about 90 hours in total. The dataset used for training spans just 24 hours, which is extremely small compared to foundational models. So let's move on to latent sync, which is based on a diffusion model. As you can see, the base identity is preserved much better in this case. And while this is the abstract, we'll go over its details a little bit later. A diffusion model, as shown at the bottom of this slide, works by having a neural network predict small changes to a noisy or partially denoised image at each step. After around 10 to 20 such transformations, the model gradually reveals a clean, detailed image. On this slide, we see a simplified overview of the latent sync approach. A reference frame and a masked frame are passed through a variational autoencoder, VAE encoder, while MEL spectrograms from the input audio are fed into the diffusion model. The resulting latent representations are then decoded by the VAE decoder to generate the predicted frame. So that was the simplified version of the pipeline, and here we see the process in more detail. It includes a whisper encoder and SyncNet supervision, and they place particular emphasis on the SyncNet module. SyncNet basically outputs a synchronization confidence score. We feed it the estimated frame and the MEL spectrogram from the audio, and it evaluates how well they're aligned. It's trained on video clips where the audio and frames are either well synchronized or misaligned. If they match, it learns to output a high confidence score. If not, it returns a low score indicating poor alignment. They explored two approaches, and as you can see, the method where they feed the full image frames into SyncNet, approach A, performs better. You can also see how they apply an affine transformation. They select 3 facial landmarks, the centers of the left and right eyes, and a point on the nose, and use these to align the face vertically. This ensures the network always sees faces in a consistent, upright orientation, which helps because the model was trained that way. Later, after generating the prediction, the image is inverse transformed and inserted back into the original frame. They're also proud of their efforts to address the shortcut learning problem. In audio conditioned diffusion models, the network can sometimes cheat by inferring the masked lip region using only visual cues from the surrounding face, like the position of the eyes, nose, or facial muscles, instead of relying on the audio. Surprisingly, this can be learned very quickly, but it starts to interfere with the intended audio-to-lip synchronization. To combat this, they apply SyncNet supervision. In addition, they use temporal representation alignment, TREPA, to improve consistency across time, making sure that the distribution of temporal features is similar between the original and generated video sequences. So let's take a moment to talk about the metrics. Here you can see a table, which, of course, was compiled by the MuseTalk authors, and unsurprisingly shows MuseTalk achieving the best results. The FID score shown here refers to the Fréchet inception distance, a metric that measures the similarity between two distributions. One distribution is made up of the generated lip-synced images, e.g. from MuseTalk, and the other comes from ImageNet. The lower the FED, the better. For ground truth, FED is essentially 0, although that's a bit debatable. If we were comparing ImageNet to another dataset, the FID wouldn't be 0, but would still be low. What's strange here is that the MuseTalk authors claim their FID score is better than Latent Sync's, even though visually, Latent Sync appears to have higher quality. This suggests there may be some discrepancy between quantitative metrics like FIDI and actual perceived visual fidelity in this case. What's even more interesting, and a bit strange, is that when we look at the FID metric reported by the Latent Sync authors themselves, their model actually outperforms MuseTalk on the same dataset using the same metric. You'll notice both tables refer to HDTF, one as HTDF, which is just a typo. If you check the papers, it's clear they're using the same dataset. I also investigated the different versions of the papers, version 1 and 2 for Latent Sync, and all 3 versions for MuseTalk, and this discrepancy isn't due to conflicting versions. The results seem internally consistent within each paper, but they don't align across papers. Another interesting observation is how some of these metrics change from one version of the paper to the next. For example, in Latent Sync, version 1 is shown at the bottom and version 2 at the top. The FVD score changes quite dramatically, from 192.74 down to 162.74. That's a significant improvement. And interestingly, it's exactly 30.00 points lower, which feels surprisingly neat. This value is repeated consistently in the paper, so while it might still be a typo, it doesn't look like one at first glance. You'll also notice that version 2 includes an FID score, which was missing in version 1. Personally, I think the best metric is still subjective evaluation, what the target audience actually perceives. The most meaningful comparison comes from a blind test, where viewers are shown videos from different models without knowing which is which, and asked to rate the quality. This kind of human preference score, like a mean opinion score, MOS, is probably the most trustworthy metric. Thank you for your attention.